Hey, Steve Basic Architect. Yeah, we are back for the attack. Yeah, we're back in our Vibe studio. Got the Vibe board fired up. Yeah, we're going to continue that conversation. Our very first passive house, we're talking about the garage. We're going to talk about the fact that it's in a high wind zone. And what did we do to the idea that the fact that it was in the high wind zone, but more importantly, how did we illustrate that or provide documentation to build appropriately for where we're at? So let's check it out. Quick picture of the house. You remember, quick reminder. Designed it in 2009, built it in 2010. Number 5, I believe, passive house in the nation. Climate zone 5. Damn near zero energy too. Right? We were very, very close. Ran out of roof. If we did it today, I'm guessing those are panels that were probably 250 watts. We're probably 425 now, so we could definitely hit it today. With it, we did a detached garage, you can see, displaced from the house here. But just like the house, if you remember, you know, the house had very specific drawings done for wind bracing and shear. We're in a high wind zone here. What's that? Right? In excess of 120 mile an hour winds, or design wind is 120 miles per hour. So it can get pretty feisty out here. It's right on the water. They are only one-story structures, so we have to protect them, but we don't have to get necessarily carried away. It's a very simple gable structure. Right, so we have some nice long rectangular walls here. The beauty of the fact that it's a garage means we have one window, but we have a lot of wall. And a lot of wall there on both sides. So that handles wind in that direction. But wind in this direction, yeah, we don't have a whole lot of wall. But we have a whole lot of opening. And it's that ratio of opening to wall space and opening to wall space that is of concern when it comes to wind, right? Here, we have an awful lot of wall so that when the wind blows on this wall, we can resist it with systems. Let me switch colors here. We can resist it with systems in this wall. When the wind blows on this corner of the house, we only have a little bit of wall there and a little bit of wall there and a little bit of wall there to provide any resistance, right? This thing wants to do that. Right? And this wall wants to go like that. When the wind blows on that corner, it wants to rack, right? So, pull up the elevations. And like I said, here, it's pretty easily noted on the sides. We have a door now, and we have a window. This wall is exceptionally good in shear because we have a whole lot of wall and we have very little bit of window. So when the wind blows on that corner or that corner, we have a lot of resistance. Come on, Blue. We have a lot of resistance pushing back there. But up here, we have a whole lot of wall. Here, we have a door, but we have very little wall. This is on the order of 2 feet. That's about as small as we want to get it. So we do have, again, when the wind blows here, or here, we have a whole lot of resistance here, but here, this thing wants to deform right there. So we have to pay some attention to that. On the gable ends here, again, very similar. We have, you know, nice big wall panel there, and especially when these wall panels are tied to the corners, right? The corner is what really, when this blows here and blows on this wall wants to overturn, but being tied into that corner makes it a lot more effective than, you know, just a wall in the middle of the wall, because that space, let's say in the middle of the wall here, there's nothing that it's laterally attached to. This wall here, as it tries to deform, it's also attached along that line. So not only do you have to push that wall over, but that wall that runs down the side here, which in this case is this wall, you have to deform all of that wall as well as that front wall to get that to move in that direction. So we're good there. The biggest problem, and it always is the front wall, right? And it's because we just have these small little spaces here, but and these large doors here. And when the wind blows here, right, we get some pushback, but it's a little bit. These doors really want to go like that and deform, and it wants to push over. So we have to develop a system that can push back a little harder there. But the problem is that we don't have the luxury of a lot of wall to develop holding that building down to the foundation, right? When the wind blows on this wall, so you understand, and this wall wants to deform, it basically wants to lift off the foundation there, right? It wants to tear and get blown away. We've all seen Wizard of Oz, right? See how the house goes in a very high wind situation. So anchoring that wall is important, right? But the next mode of failure is when it tries to deform, we have our structural sheathing. Well, the structural sheathing, a couple things can happen. When it goes to deform, the structural sheathing, maybe the nailing pattern isn't enough, and the panel just rips off the 2x frame. And then we have failure mode. If it's nailed off, if you sit there and say, wow, I'm not going to worry about that, Steve. I'm going to nail the hell out of it. I'm going to put a nail every inch. Well, the problem with that is by putting a nail every inch, then you're creating almost a zipper-like effect. When the wind blows, now the OSB doesn't pull the nail out. It just tears across that nail line because it's so perforated, right? Think of those notebook sheets that come pre-perforated. A slight tug, and I can basically tear it off. Well, we don't want to create that situation in our garage here either, or in our house at any shear type moment. So it's a delicate balance to the size of the nail, the spacing of the nail, so we don't create a zipper, as well as the nail spacing to the edge of the panel, right? So if I have a 2x plate and I do a nail every inch, then I'm going to create a zipper-like effect. If I have the 2x plate and I do a nail every 3 inches in that panel, then a couple things can happen. One, I can tear the panel along the line of the nail, similar to that if the wind is strong enough, or I can have a failure mode where this piece, the nail will just rip out there if this is nailed too close to the bottom, right? So a lot of times in some high wind situations, we'll actually put a double sill in or use a 4x4, because then I can put another nail up here, another nail there, And you can see how that added strength, but also this added distance keeps us from that kind of tear out mode failure there. But let's take a look. If I take the elevations that I have drawn here and I take all of the cosmetic stuff off and then just look at the sheathing, then I have these wind bracing details. So these are just sheathing details, and you can notice here there's a bunch of things happening, right? You can see each of the individual panels is called out by the big X, and then we have a line of blocking in there, solid blocking at panel edge. These here are 1/2 inch OSB continuous nail spacing, 3 inches on center at the field and 6 inches, or at the perimeter 3 inches, and then in the field 6 inches. So those are 6 inches, but here it's 3 inches and here it's 6 inches. Notice also, somewhere I have it, yeah, Simpson strong tie, we added in some metal strapping. And that metal strapping, we'll do that in purple, you know, that goes from top plate to bottom plate. And that is nothing more than kind of a lead bracing. It's the modern version. It's a metal strap. You can get it, it's a T-shaped. You can also get it in a flat and bend it around the 2x4. So if I have my bottom plate here and that strap is coming down, it actually increases the strength to bend it under that plate, right? I mean, think about it. If you took something and you just nailed it there and it stopped here, then I could pretty much rip it off the nail. But the fact that I bend it around the corner and then nail it also, now I have to, not only do I tear it, I got to pull it out from around the corner. So I get that additional resistance happening there. The other thing to notice is that notice each and every anchor bolt is called out. And those are called out 1/2 inch diameter, 4 inches on, or 4 feet on center, and within 12 inches of the corner. So we have to have an anchor bolt within 12 inches of the corner, and then they're 48 inches. But also notice I put the additional one on that first panel because the corners are just so important to get it right. We want anchor bolts on that one panel there, right? And you can see it again there. But the real kind of anomaly, if you will, is the front. And it always is, right? Again, that term aspect ratio comes in, and that is this distance versus that distance, right? And the closer you can make this 1-to-1 or even more, right? This is 3-to-1 or 2-to-1, something like that. The minute you get in this is 0.5-to-1, 0.25-to-1, 0.20-to-1, right? 2 feet to 8 feet. It becomes a big time challenge. So notice we've done a couple things here. We'll just go through these notes on what we call the portal frame, right? The garage door portal being what we're referencing there. 4x4 post on each side. So we end there and a 4x4 there. And that's to get 2 rows of nailing on that 4x4. So we increase the attachment of our shear panel to our wood frame. We have our anchor bolt there, but in addition to the anchor bolt, note that we have these hold downs in each of the corners, and I'm sure somewhere I'm going to call those out and we'll check it out. But the hold downs are, just think of them as anchors on multi-steroids, right? They're significantly, I'm not going to put a number together to it. I'm not a structural engineer, but I will say it is a lot stronger than the standard anchor bolt that is going in there. So we have those hold downs. Those hold downs also go to the 4x4, right? Are you seeing what's happening here? Our foundation's connected to the hold down. Our hold down's connected to the 4x4. The 4x4 is connected to the header, which drags that shear into the system. So here you can see Simpson HWT 187, Simpson strong tie, 3/4 inch anchor bolts, fill all fastener holes, 2 per panel, 6 total, right? So those are going in there. Interior face of garage walls, portals, OSB to extend to exterior face of exterior wall prior to framing walls on the garage. Also notice we have 1,000 pound straps, Simpson LSTA. They're just a flat metal strap, interior face of framing. And those are happening on each side of the door there. And then of course, full length header going all the way across. So it's one header. So you can see, and we'll pull out big red here. We have our foundation. We're connected to the foundation. We are also have these hold downs and 4x4s here. So that's a pretty rigid system, right? We're not tearing that off the foundation. Not with those hold downs there. Those hold downs go up. There's probably something like 20 or 30 screws or nails that go into that hold down and attach it to the 4x4. So it is an extremely robust connection there. Those 4x4s go up. On the inside, we have that metal strap, right? We'll do that one in green. We have that metal strap there, but also the fact that this header is captured by this panel and that panel. This thing wants to deform. The header keeps that in nice alignment there. And that's, you know, basically portal frame construction, if we wanted to refer it to its common name. And then of course, everything up here is certainly helping, but it's really, where do these panels connect to the foundation? And more importantly, how do they connect to the foundation there? So, you know, like I said, you can see in the drawing that that front is the one that has the most notes, the most of anything happening. And again, it's because it is the one that's at the highest risk because it has those very large openings. When we have, you can see here, right? We have 12 feet of shear panel there. We have over 12 feet of shear panel here, right? Or roughly 12 feet. And the window's in the middle. So it makes for a very, very robust system there, just kind of being business as usual. You don't see the needs for any hold downs, any 4x4s in those corners there because we meet the shear requirements by virtue of having a large shear panel. When we don't, then the loads don't change. The way we react to the loads change. And so we have to develop new systems using our good friends at Simpson Strong Tie, in this case, with hold downs and those LST straps to help us develop those systems. Now, you might have seen in some of my other projects, we can also put a piece of steel in here and make it a steel moment frame. And it does the same thing. It's just, we're switching to steel. Simpson also makes a kind of bolt-in proprietary moment frame that we can put in there that we've used on the Hilltop Aero project. I know we used it there, but a few other places. So, and they have wood and metal corrugated metal panel systems. So they have different degrees of success there. So anyways, a little talk on shear. I'm Steve Basic Architect, contributor on the Build Show. This is the Vibe Board, November 7th and 9th, and 7th through 9th this year. Yes, 2024. Build Show Live, Austin, Texas. Be there. Get to meet all the contributors. If you're still looking for more, Instagram, LinkedIn, Facebook, TikTok, I'm on all of them. Post mostly on Instagram and LinkedIn. I do some Facebook and I do some TikTok. It's, you know, time is my nemesis. And then, of course, you found me here on YouTube. You know what I'm going to say. Smash that subscribe button. Tell all your friends. I'm Steve Basic Architect. Until next time, long live our buildings.